Hello, welcome to this massive open online course on probability and random variables for wireless communication. In the previous module, we had looked at experiment and outcomes of the experiment and the samples, concepts of sample space, events and other things. Let us now start with a formal definition of the axioms of probability. Let us now start with a formal definition of the axioms of probability. There are three axioms of probability which are very important, and I am going to list these. So, I have the three axioms of probability. I have axiom 1, which states that the probability. So, what is the probability? So, let us start with the probability for a formal definition. The probability measure of any event A, the probability is a measure, the probability of the probability measure of any set A satisfies the following axioms, and those axioms are as follows. First, let us have the first axiom, that is the probability measure of any event A is greater than or equal to 0. The probability measure of any set A is greater than. So, we are saying the probability is a measure, the probability is a measure which is defined for events A of the sample space S, and it follows some basic axioms. The first axiom is that this probability measure is non-negative, right. This probability measure is non-negative, which basically says that the probability of any event A is greater than or equal to 0. I will now write axiom 2, which is that the probability of the sample space, the measure of the entire sample space, the probability measure of the entire sample space, that is, if I look at the entire sample space, the probability measure of the entire sample space is unity or 1. And the third axiom is basically that if I look at the third axiom is that probability of A union B equals the probability of A plus probability of B if A intersection B is the null event phi, or basically A comma B are mutually exclusive. So, we are saying that if two sets or if two events A and B are mutually exclusive, that is A intersection B is the null event, A intersection B is equal to phi, which is the null event, then the probability of the union of these two events, probability of A union B, the probability measure of A union B is simply the sum of the probability measures of A and probability measure of B. So, probability of A union B equals probability of A plus probability of B if A intersection B is basically the null event, or A and B are mutually exclusive event. So, we have three axioms of the probability that the probability measure satisfies. First is that the probability measure is non-negative. The probability A, or probability of any event A, PA, is greater than or equal to 0. The probability of the sample space S is equal to 1. and the probability of A union B equals probability of A plus probability of B if A intersection B equals phi or A and B are mutually exclusive events. Okay. So, now using these probability axioms, let us look at some basic properties. First, basic properties which follow from the probability axioms. Note that I have from my previous proof, I have S, as we have seen in the previous model, the sample space S, that is S is equal to any set A union A complement equals the sample space. Further, any A and A complement are also mutually exclusive, that is what we saw in the previous module. Therefore, I have 1 which is equal to the probability space, probability of the sample space from the axioms, which is equal to the probability, because S is equal to A union A, this is equal to A union A complement, but A and A complement are also mutually exclusive. Therefore, from the third axiom, this is probability of A plus probability of A complement. This follows from the third axiom, and this is therefore also, now you can see this implies that probability of A equals 1 minus the probability of A complement. But once again, from the first axiom, I have probability of A complement, from the first axiom, I have probability of A complement is greater than or equal to 0, which implies probability of any set A equals 1 minus probability of A complement is less than or equal to 1. What we are seeing is the following thing. We said the probability of A complement is greater than or equal to 0, and probability of the set A is 1 minus the probability of A complement. Therefore, probability of the set A is less than or equal to 1, and therefore, together with the first axiom, we can now say that the probability of any set A lies between 0 and 1. So, for any set A or for any event A, we must have 0 less than or equal to probability of the event A less than or equal to 1. Probability of A is greater than or equal to 0 from the first axiom, and now we have derived that the probability of any event A is less than or equal to 1. If we put them both together, we have the result that the probability of any event A must lie between 0 and 1. That is the first result that we have, that is the first important result that we have, that is the probability of any event A lies between 0 and 1. Let us now look at the next result, that is I have now the next result is as follows. We know that the empty set, that is, if I take the union of the sample space with the null event, that is again the sample space, correct, and if I take the intersection of the sample space and the null event, that gives the null event, because the null event does not contain any event. So, its intersection with any event, in particular intersection with the sample space, is again once again the null event, because the intersection is basically sample points which are both in the sample space and the null event, and the null event does not contain any sample points. Therefore, the intersection is the empty set or the null event. Now, again using the second axiom, I have 1 equals the probability of the sample space, which is equal to the probability of S union the null event. Now, you can see S intersection null event is the null event, which means S and null event are disjoint, which is equal to probability of S plus the probability of null event, and probability of S we said is equal to 1 from axiom 2. So, this is equal to 1. So, we have 1 is equal to 1 plus the probability of null event, which means the probability of null event equals 1 minus 1 equals 0, which therefore, we have our second property that we have derived, that is the probability of null event, that is the probability of null event is 0, or this is also basically an impossible event. The probability of null event is 0, which is also known as an impossible, this is also known as an impossible event. Okay. And 3, again some other properties which are not going to derive elaborately. 3, if A and B are any events, then probability of A is less than probability of B if A is a subset of B. That is, the probability is a measure, and we are saying if A is a subset of B, that is, if A, the event A is a subset of event B, then the probability measure of the event A is less than or equal to the probability measure of B, correct. And 4 is another important property which I would like to prove, which is the following thing: if A and B are any events, A comma B are 2 events, then I have probability of A union B equals the probability of A plus the probability of B minus the probability of A plus probability of B minus the probability of A intersection B, and this can be seen as follows. For instance, if I have 2 events A comma B, let us say I have 2 events A comma B, this region, of course, this region, if I look at this region is A intersection B, and this region, now if I look at this region, that is the region which is present in B. So, this is my set A, this is my set B, this is A intersection B, this is the region which is present in B but not in A, and this region is therefore B intersection A complement, and this is the region which is present in A but not in B, therefore, this is the region A intersection B complement, correct. So, I have 2 sets A and B, or 2 events A and B, right, and I can decompose these 2 events A and B into 3 distinct regions. One is A intersection B, that is the overlap between these 2 events. A intersection B complement, that is all the sample points which are in A but not in B, and B intersection A complement, which is all the sample points which are in B but not in A. And you can see from this picture that these 3 events, A intersection B complement, A intersection B and B intersection A complement, these are basically, you can see that these 3 events are mutually exclusive, that is A intersection B complement, A intersection B and B intersection A complement. These you can clearly see these are mutually exclusive events, because they do not have any overlap, and therefore naturally it follows that I have naturally it follows that I have P of I have the probability of A union B equals, and further the union of all these is basically A union B. Therefore, I have the probability of A union B is the probability of A intersection B complement plus the probability of A intersection B plus the probability of B intersection A complement, correct. So, we what did we say? We said that any two sets A and B can be represented as as three distinct parts, that is A intersection B complement, A intersection B at B intersection A complement. These are disjoint, and further their union is equal to A union B. Therefore, the probability of A union B is simply the sum of these three distinct mutually exclusive components, that is probability of A intersection B complement plus probability of A intersection B plus probability of B intersection A complement. Now, let us look at this event probability of A intersection B complement. If you can see A intersection, now if you look at A, the event A is the union of A intersection B complement and A intersection B. Therefore, I have probability of A equals probability of A intersection B complement plus probability of A intersection B, which implies the probability of A intersection B complement equals the probability of A minus the probability of A intersection B. Further, if you look at this, similarly probability of B intersection A complement equals the probability of B minus the probability of A intersection B. Now, substituting this probability of A intersection B complement over here and probability of B intersection A complement over here, I have the probability of A union B, which is equal to the probability of A minus probability of A intersection B plus probability of A intersection B plus the probability of B intersection A complement, which is the probability of B minus the probability of A intersection B, which is therefore equal to the probability of A plus the probability of B minus the probability of A intersection. So, the probability of A union B equals probability of A plus probability of B minus the probability of A intersection B. This is one of the fundamental results in probability, that is the probability A union B of any two events A and B is the probability of A plus the probability of B minus the probability of the intersection of these two events, that is the probability of A intersection B. Let us take a simple example to understand this. Let us look at a simple example. Let us go back to our Emery PAM, Emery pulse amplitude modulation. Let us take a simple example to understand this. Let us go back to our pulse amplitude, Emery pulse amplitude modulation, which we introduced in the previous module. This is our Emery PAM, and let us say that we have the following probabilities. We have the following probabilities for the sample points, the various sample points. Let us say this probability of minus 3 alpha is basically 1 over 8, probability of minus alpha is 1 over 8, probability of alpha is 1 over 4, probability of 3 alpha is half. Therefore, now if you look at the sample set, probability of the sample set is 1 by 8 plus 1 by 8 plus 1 by 4 plus half, which is equal to 1. So, the probability of the entire sample space is equal to 1. So, that satisfies the probability axiom, that satisfies the probability axiom. Further, let A be the event minus 3 alpha comma alpha, then the probability of the event A is the probability of minus 3 alpha, which is 1 by 8 plus the probability of alpha, which is 1 by 4, which is therefore equal to 3 by 8. Let B be the event, let us define another event B, which is equal to alpha comma 3 alpha, which implies the probability of B is equal to probability of alpha, which is 1 by 4, versus probability of 3 alpha, which is half, which is equal to 3 by 4. Now, if you look at this, I have probability, I have A union B, which is equal to, from this, which is minus 3 alpha comma 3 alpha, implies the probability of A union B is given as, probability of A union B is the probability of minus 3 alpha, which is 1 by 4, plus the probability of alpha, which is, well, which is this is probability of minus 3 alpha, which is 1 by 8, plus probability of alpha, which is 1 by 4, plus probability of 3 alpha, which is half, which is equal to 7 by 8. Probability of A intersection B is, now A intersection B, you have to look at A intersection B. A intersection B is basically, we have minus 3 alpha comma alpha intersection alpha comma 3 alpha, the event B, which is equal to the only common sample point is basically alpha. Therefore, probability of A intersection B is simply the probability of alpha, which is equal to 1 by 4. And now, probability of A plus probability of B minus probability of A intersection B is simply probability of A as we have derived previously, that is 3 by 8, plus probability of B, that is 3 by 4, minus probability of A intersection B equals 1 by 4, that is so 3 by 8 plus half, which is equal to 7 by 8, which is equal to probability of A union. And therefore, what we are seeing from this example, is that probability, indeed probability of A union B equals probability of A plus probability of B minus probability of A intersection. So, what we have seen is, we have considered this simple example from Emery PAM, Emery pulse amplitude modulation for a wireless communication system, and we have derived that the probability, and we have shown, simply we have verified the result that we had derived earlier, that is the probability measure of A union B is the probability measure of A plus the probability measure of B minus the probability measure of A intersection B. So, let us conclude this module with this example. We will look at other aspects in subsequent modules. Thank you very much.